Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be doing a crash course on the topic of dynamics for Cambridge A-Level Physics 9702. So this counts as a topic in AS Physics in the first year of your 2-year A-Level Physics diploma, and the topic of dynamics comes right after kinematics. And again, in this crash course, I'm just going to cover the important concepts very basically. But again, the onus is on you to make sure that you are studying to understand the deeper underlying applications of the concepts in dynamics. And so when we did the last crash course on kinematics, we talked about how things move, but we didn't really care about why they were moving in that way. We just really were cared about how they would move as we evolve with time, as the system evolved with time. But in dynamics, we actually are worried about what causes things to move. And so the first thing we need to talk about is actually, in the build-up, I'm going to talk about Newton's laws, and then we'll branch out a bit to see some other concepts in dynamics. So basically, what happens when an object moves is it must be pushed, which kind of makes sense. If you see an object stationary and you push it, it moves, provided that you can overcome the friction and the resistor forces and so on. So what we are cared about now is, well, the thing moves, but the thing moves because I push thing. And if I push thing and thing moves, then I'm interested in how my pushing relates to how thing moves. And this push, or sometimes a pull, we call a force. If you haven't seen what a force is already, a force is a vector. And a force is something that will cause an object, a massive object, to move. Provided there isn't any other force. So in the absence of other forces, a force will make an object move, and we'll talk about how that object will move when that force is applied. But a force is a vector. It's a push or a pull in a certain direction. If I push the box to the right, the box moves to the right. If I pull the box to the left, the box moves to the left. And so that's what we really cared about in dynamics, where the motion comes from. So how does us pushing or pulling then translate into thing moving? We also talk about things like resistive forces that oppose motion. So I push box, box moves, but box gets resisted by floor. The thing I push is resisted as I push it against the floor, and it's very difficult for me to move the box across the floor, especially if the floor is quite rough, or the bottom surface of the box is quite rough. And this is also a type of force which is called friction, and friction is a resistive force. So I'm not going to list all of the resistive forces, like viscous drag and so on, and air resistance, but there are different types of resistive forces that basically a resistive force is any force that opposes the desired motion of the object. I want the object to move to the right as I push it, but the friction acts to the left and opposes my force. And so basically, before we start Newton's laws, we have to understand what the idea of forces are. And I'm just going to assume that you do get forces and that it's not something that's kind of like brand new to you. But our good friend Uncle Newton did describe 3 laws of motion, and very simple laws of motion for objects, and we use these laws of motion as sort of the basis to solve our problems. Now, Newton's laws are not the only laws we can use to solve problems in mechanics, but for us, we're going to stick with Newton's laws, especially for now. Talk about Newton's laws as the way of solving problems when things are going to be moving. And so Newton's first law, and you should know how to state the laws, all of them, and state them as accurately as possible. Try not to add in your own words or remove words for convenience, because it can change the meaning. But Newton's first law says that every object continues in its state of rest, or with uniform velocity, meaning constant velocity, unless it is acted upon by an external, or acted upon by a resultant force, rather, by a resultant force. So this is what Newton's first law says, and you need to be able to state this in as close as possible to these words as you can. So an object will remain, if it's at rest, it will remain at rest. If it's moving at constant speed, it's going to move at constant speed unless there's some resultant force acting on the object, meaning there's a force that's unbalanced on the object. And this kind of makes sense, although it doesn't really make sense on Earth, because I can push a box and make it move with a certain speed, and then it's very shortly going to come to rest when the friction opposes the motion. But if I were out in space and I threw a baseball in empty space in vacuum without any forces around to influence the motion of the ball, after I threw the ball, after I applied the force to cause the ball to move, it would have some velocity, which it would then continue to have as it floated through space until it were attracted by some gravitational field or collides with something else. But it would just move with constant velocity because there's no resultant force acting on the ball, or negligible resultant force acting on the ball as it moves through space. So Newton's first law is not all that difficult, but it's profound, and we use it to answer some of the most difficult problems in the universe. And it's sort of, Newton's second law sort of builds on Newton's first. And usually Newton's second law is sometimes poorly stated and poorly understood. We could ask university undergraduates what they thought Newton's second law is, and they would say F is equal to ma, which is not the 100% wrong answer, but it's not the right answer. F is equal to ma is a mathematical formulation of Newton's second law, but doesn't really do justice to Newton's second law in totality. So Newton's second law says that for an object of constant mass, so we are going to assume that mass remains constant in all our applications of Newton's laws. So for any object with constant mass, its acceleration is directly proportional to the resultant force acting on it, or acting on it or applied to it, whichever you feel is better. So the first law says if there's no resultant force, you're going to stay at rest or you're going to move at constant velocity. The second law says, well, what if there's a resultant force on an object? Well, then the object will accelerate, and that acceleration will be directly proportional to the resultant force that's applied to the object, and inversely proportional to its mass. I think that's also should be part of the definition, and inversely proportional to its mass. So from here, you can sort of put together the mathematical expression. You can sort of piece it together from this statement. But basically what it says is F is equal to ma. But F is a vector, force is a vector, so too is acceleration. So simply saying F is equal to ma doesn't give the full idea. The force and the acceleration, since they are both vectors and mass is not, mass is a scalar. Mass is just giving the size of, it's just adding an extension to the size of the acceleration to give us the force. This means that the force and the acceleration must be in the same direction. Because there are two vectors in the same equation, and we can't have one vector equals to a number times another vector, but the two vectors are pointing in different directions. We don't really cover vectors that well in A-level physics, but you get the idea. And so here you can see that if the mass is constant, the acceleration is proportional to the force. I push harder, the box accelerates faster. And the acceleration is inversely proportional to the mass. If I push with a constant force, then the heavier the object, the less the acceleration. Again, I can push a box across the floor, but I'm going to struggle to push a truck across the floor. So what does this look like? This is box. Box has mass m. I push box to the right with force F, and assuming there's no resistor forces, no friction, etc., box accelerates to the right as well, same direction. And the unit that we use to measure force, this push or pull, is called the Newton, uppercase N, which is the symbol. And you can see that F is equal to ma, which is the mathematical formulation of Newton's second law. So mass is measured in kgs and acceleration is measured in meters per square second. So a Newton is equivalent to a kg meter per square second. What this means is if I push with a Newton of force, then a 1 kg, so it gives 1 kg and acceleration of 1 meter per second. That's what 1 Newton of force basically means. So if you want to picture it, picture a 1 kilogram box. I push with a force of 1 Newton. It accelerates at 1 meter per square second. That's what a Newton of force is. And remember, Newton, although named after a person, the unit of measurement is a common noun, so it's lowercase n, Newton with a lowercase n. And so this is basically Newton's second law in a nutshell. And we look at some more complicated examples with angles and so on. But basically, that's what Newton's second law says, mathematically and as a statement. Newton's third law also, hugely important. Those of you that are writing your full A levels, you would have already started your papers. And you know that you apply Newton's third law in quite a few scenarios, in magnetic fields and gravitational fields and so on. And so although we say it's classical physics and not modern physics, and Newton's laws have since been sort of disproved, still works perfectly fine on small-scale systems on the Earth and so on. And Newton's third law says that whenever one object exerts a force on another, or when the first object exerts a force on the second object exerts an equal and opposite force on the first. So when an object exerts a force on a second object, the second then exerts an equal and opposite force on the first. I push box with my hand, and box pushes back on my hand. Remember that there are two forces here, but they're both acting on different objects. A common question is, well, if all forces have an action-reaction pair, we sometimes call this the action-reaction law. For every action, there's an equal and opposite reaction. It doesn't do the justice to the actual law. But if there's an action-reaction pair for every force, then shouldn't all forces cancel out and there not be any resultant force on anything? But remember, when I push on the box, I'm considering all of the forces acting on the box, the friction, my push, etc. But on my hand, there may only be one force, that is the force of the box. And so these two forces act on different objects, not on the same object. Hence, we can still have unbalanced forces and the universe is fine. So I'm going to do a non-example of what an action-reaction pair is not. So also a common misconception. I tend to be favoring boxes today. It seems like the easiest example to work with. And I place box on floor. Well, it doesn't have to be on the floor. It could be on the surface of a table. And I know there's a reaction force that acts on the box. It's a force that the table surface exerts upward on the box, and the earth pulls the box downward, and so it has a weight mg. And since this box is not moving, N is equal to mg. The normal reaction force acting perpendicular to the surface of the box upward balances the weight downward. But however, this is not an action-reaction pair. Well, firstly, they're not of the same type. The reaction force, the normal reaction force, is a contact force. But the weight is a gravitational force. So they're not of the same type. Secondly, they both act on the same object. They're both acting on the box. So what we must remember is that the action-reaction pair, now some of you may already know this, but for some of you it might be like, hey, wait a minute. I always thought that the action-reaction pair would be normal and weight. But the action-reaction pair must act on two different objects. So the action acts on one and the reaction acts on the other object. Okay, so what's actually happening here? What is the action-reaction pair? Okay, let's just do one pair. There's actually going to be two action-reaction pairs, but let's do one. So I have box. I'm going to exaggerate the size of the box now, just so it's easy to see. And there's a force acting downward. And this is the gravitational force. This is the weight of the box. The gravitational force that the earth exerts on the box. And we call this weight. So you have a weight because the earth is pulling you towards its center. Then I draw, believe it or not, this is the earth. Don't ask why they are roughly the same size. Again, not drawn to scale. But the reaction to the gravitational force of the earth on the box, believe it or not, is the gravitational force that the box is exerting on the earth, of the box on the earth. So the earth pulls the box to its center, which is the weight, but the box rather pulls the earth to its center, which is the reaction to the weight. It can't only be that the earth is doing all the pulling. If you were to jump, do a standing vertical jump right now, you'd be pulled back to the center of the earth. But at the same time as you jump, you would pull the earth towards your center as well. It's just that the earth is much larger than you are, it should be. And so the earth does very little moving where you do a lot more moving. And so this is an action-reaction pair. So just again, many of you may already know this, but it's important to remember what an action-reaction pair is. And that will save you a lot of worry when you're thinking about the really difficult conceptual problems that you may encounter. Now, the next thing we want to talk about is momentum. And again, momentum has a very specific meaning in English, but a very specific meaning in physics. And we don't give it sort of, well, at least for now, when we study physics at this early level, we don't give it a very detailed explanation. We simply say it's a product of mass and velocity. And then when you study further physics and you define things like energy, momentum, tensors, and so on, then it becomes a lot more complicated to understand what it means. But for now, it's simply the product of mass and velocity. And if I take a scalar quantity and multiply it by a vector, I get another vector quantity. So momentum, just like velocity, is a vector quantity. And it's defined by the symbol P, and P is obviously equal to m times v. And the unit of measurement for P, for now we're going to use the unit of measurement kg meter per second. We don't have a derived unit that we use for momentum for now, So we'll stick with kg for mass and meter per second for speed. Simple. But also, there's a way of writing Newton's second law in terms of momentum as well. Remember we said F is equal to ma, mass times acceleration. But acceleration is the rate at which my velocity is changing, m delta v by delta t. But m delta v for an object with constant mass is its changing momentum. And so this means that the resultant force on an object, I should technically be saying net force or resultant force. It's a good habit actually to be writing F net to F resultant, but we assume it to be understood. F is delta P by delta T. And this is actually another form of Newton's second law. F is equal to ma is F is delta P by delta T. So the rate at which your momentum is changing is the net force on an object. If you think about it, if there's a net force acting on an object, it's accelerating, its state of motion is changing, so its momentum must be changing. How rapidly its momentum changes tells us how great the force is. Again, kind of makes sense. If I push the box with a really high force, it moves, it changes the state of motion very rapidly. If I apply a very small force, it changes its momentum or its velocity very slowly. And so the basic problem-solving method that you will use, well, if you intend to do physics at any point after A levels for the rest of your life, I think that will be sort of the most useful when using Newton's methods to solve mechanics problems are free body diagrams. There are other methods of solving problems in mechanics, Lagrangians and so on, which you'll learn later on. But for Newton's methods, we look at all the forces acting on objects. And when we apply Newton's laws, we have to have forces. Since forces are vectors, we can draw what we call free body diagrams. And believe it or not, I'm going to draw another box on a flat surface. This is also a flat surface. And I'm going to assume there's 4 forces acting on this box. There's a normal reaction force. Again, I'm just going to assume that this box is some center of mass point, and the forces are acting on the center of mass. But it's not actually true, they're acting at different points in the box. But there are 4 forces acting on this box. The normal reaction force, I'll call it R, acting upward. The weight W acting downward. The box has a mass M. It's being pulled to the right. It's actually being pulled up and to the right by a force P. And this force acts at an angle of theta to the horizontal. And it starts to move, so it has acceleration A. But the surface is a little bit rough, so there's also a force acting to the left, which is the frictional force, which I'll call little f. We sometimes use a small letter f to denote frictional forces. Now, a free body diagram is a very good way of identifying all the forces acting on an object and then making it easy to apply Newton's laws of motion. So if I look at my force diagram, I can see there's no motion up or down, which means that there's a balance of forces upward and downward, which means that the weight is equal to the reaction force R. The box is not moving up into the air or down through the plane, to the surface of the table or whatever it is. But it is accelerating to the right. So there must be a net force acting to the right, because that's what Newton's second law says. Net force acting to the right, object accelerates to the right. So everything in physics requires us to set up equations so that we can understand mathematically what's happening. When we understand mathematically what's happening, we can then translate that back to a conceptual understanding of the problem. So if I assume, or if I consider this box P being pulled up and to the right, the upward pull, actually what I should say here is W is equal to R plus Py, a y component of P. So this vector P, completely ignored vector P here, as a y component and an x component. So the weight is being matched by the upward pull of P and the reaction force R. And so there's no motion up and down, so we can equate those forces. So I've set up an equation just by looking at the problem. This is how we get mathematics from conceptualization. Now, only the horizontal component of P, Px, is responsible for the acceleration, because that's the only component of the force P along the direction of motion. So Px minus the frictional force must be the resultant force. The resultant force must be to the right. And Newton's second law says the resultant force must be equal to ma. So what this means is that P cosine of theta, you can do the trigonometry if you like, P cosine theta minus F is equal to ma. I've now set up a system of two equations just by drawing a free body diagram. Is it required? Not at all. Is it helpful? It always will be. You could go into university, undergraduate university physics, and you will still find this a very useful method, because problems can get very complicated the more and more objects we add. And so each object, break it up into a free body diagram, and then use that to set up your system of equations. Is it the cleanest method mathematically? Probably not. But is it very easy to conceptualize? Yes, it is. And it usually works for most of our mechanics problems. And so that's our understanding of free body diagrams and how to use them effectively. Now we need to move on to onto something. We're going back to the topic of momentum, kind of. And we want to talk about the conservation of linear momentum. I'm being very specific here. I'm saying linear momentum now rather than just momentum. Why is this? Because there are two types of momentum that we can study early on, and that's linear momentum and angular momentum. We aren't studying angular momentum in this course, but we are going to study linear momentum. So let's assume that I have two billiard balls, or snooker balls that are going to collide, and I want to know what happens before and after the collision. Well, there could be collision of any two objects with mass. So the object 1 has a mass m1, it's moving to the right with velocity u1. There's an object m2 moving to the left, different mass, different velocity. I'm not drawing these vectors to scale, I'm just drawing the arrows showing the direction. And this is two balls moving toward each other. Maybe we roll them towards each other, and then they collide. And when they collide over a time delta t, they both feel an equal and opposite force, because Uncle Newton he said so. Well, so the force that ball m2 feels is F to the right, and the force that ball m1 feels is the same force minus F to the left. And so this coming together of the objects is what we call a collision, when they strike each other. And then let's assume that after the collision they move on their merry way, but now in the opposite direction. So m1 has a final velocity v1 to the left, and m2 has a final velocity v2 to the right. So let's assume they come together, they collide, and they move off in opposite directions. And this is after the collision. Now, why am I doing this? Because these forces that act on the ball during the collision are, like I said, equal in magnitude. So F and F have the same magnitude, but there's a minus sign on one, so they must be opposite in direction. Another thing that's common at the time of collision, is the duration. The time over which the collision happens is the same for both of these balls. So what does this mean? So if I say that the force on ball 1 is equal to the force on ball 2, at least in magnitude, I'll ignore the minus sign for now, then the change in momentum during the collision for ball 1, delta p by delta t, is the same for the change in momentum for ball 2, delta p2 by delta t. The delta t's are the same duration for each collision. That means the change in momentum for the first ball is the change in momentum for the second ball, which means that before the collision and after the collision, the total momentum of the system is the same. So if I were to write this as an equation, I would write down all the momenta, the sum of all the momenta before the collision, m1u1 plus m2u2. After the collision, all of the momentas are m1v1 for the first ball plus m2v2 for the second ball. This expression mathematically is called a principle of conservation of linear momentum. So this is the idea that linear momentum will always be conserved. So you have to remember that when you have a collision or even an explosion, that linear momentum will always be conserved. Even if energy is not conserved, linear momentum will be conserved. Okay, so this expression is what you would write when you have a problem like this, where two balls come together, collide, and then move away. And notice I didn't put any minus signs here because, again, like you know, I prefer to put the minus signs in the values when I actually put values into the equation. So u2 will be negative 3 meters per second, for example. So this is what the conservation of linear momentum would look like in its generalized form. And so just a little heads up for what I mean. If I take the right as positive, like I conventionally do, then u1 and v2 point to the right. So they would be positive. So when I put my actual values in, and then u2 and v1 point to the left. And so if I took the left as negative, then those two vectors would be negative. And I put them into the calculation, and I can do some rearranging if I want to find maybe the final velocity for ball 2 as an example. But this is how I apply the conservation of momentum, rather the conservation of linear momentum, in order to solve some complicated or complex problems. Now there's another thing that's linked to momentum that we have to talk about called impulse. Again, means nothing as it does in English sense, but impulse is simply, very simply, a change in momentum. So it doesn't seem that complicated. It isn't for now, to be honest. But an impulse is simply a change in momentum. Any delta p is an impulse. Momentum after minus momentum before. If you were running and your speed changed, then your impulse would be your final momentum minus your initial momentum. And from Newton's second law, this is F delta t, because F is delta p by delta t. So basically, how you would think about this is, again, I'll use the idea of a ball, but this time the ball is moving to the right and it's approaching a wall. So here's a ball moving to the right. It's approaching a horizontal wall. It could be a squash ball, for example, and it has some momentum. So it has some mass, obviously, and it has some velocity. So the ball approaches a wall. It then collides with the wall, and upon collision, there's going to be a force exerted by the wall onto the ball, which will be pointing to the left. It's going to be a pushing contact force to the left, and the contact will last a time delta t. The magnitude of the force and the duration of the collision will determine how rapidly the ball will be sent back, and it'll move obviously off to the left. And our brains can do all these calculations very quickly, which makes us very good squash players or very poor squash players, and the momentum of the ball is now in the opposite direction. Now, what the conservation of linear momentum says is that the final momentum, P after, is equal to the initial momentum P before, and this must equal to delta P or rather, this means that delta P is equal to F delta T, and so the change in momentum will be the force that's applied on the ball multiplied by the duration of time that the collision lasts for. So you can actually find that you can actually determine what the change of momentum would be if you knew the force and the time of the impact. Or you could even measure the force if you knew the change in momentum. And these are the kinds of calculations our brains do when we play these kinds of sports. So the unit of measurement of delta P, you would think we could just use kg meter per second, but you can see here that it actually can also be a Newton second. So usually when there's some sort of collision or some sort of impulse, in this sense, some duration delta T over which momentum is changing and there's a force, we use Newton seconds for the symbol of, for the unit of measurement for momentum. But again, it's completely up to you. If there's a change in momentum, usually we say Newton second. If it's just the momentum of a moving object, we use kg meter per second. But those two units are interchangeable. So it's only convention that we use one in one situation and the other in a different situation. So next, I'm going to spend a little bit of time talking about collisions. Again, not too much time. This is the last bit of the topic. And it can get complicated, but it shouldn't need to. There are two types of collisions that we have. We have elastic collisions and inelastic collisions. And I'm not going to talk about them in too much detail. But an elastic collision is one in where kinetic energy is conserved. Now remember, we said that the ball hits the wall and then it moves back and momentum is conserved. Now momentum might be conserved, but it's not true that the kinetic energy will be conserved. The ball moves towards the wall, hits the wall and rebounds. It may not go back as far as it started. And that's because it will lose some of the energy as it strikes the wall, as it deforms, and some of its energy gets transformed into elastic potential energy, into heat, into sound, etc. So it'll lose some of that kinetic energy, but the momentum will still be conserved. If we also have kinetic energy conserved, we call this an elastic collision. So let's look at an example. That means if kinetic energy is conserved, then there's no loss of energy in terms of sound and heat and so on. There is technically no such thing as a perfectly elastic collision, but we can assume certain things to be elastic, like the collision of gas particles. Again, if you've done A-level physics already, you know that we say for ideal gases that the particles collide elastically, perfectly elastic. Even though technically it's not totally true, it's close enough. So before two objects collide, they would be moving toward each other, M1, M2, very similar to what we said before. After they collide, with an elastic collision, they move off in opposite directions. So V1 to the left and V2 to the right. Whereas initially U1 was to the right and U2 was to the left. So the two balls collide and then they move off in opposite directions. So this is what happens in an elastic collision. They strike and they move off. And the conservation of kinetic energy. Now, there's lots of equations that you can sort of memorize and so on, but this is the most important. Kinetic energy is conserved in the elastic collision. So you can write this equation down as your first equation. A half m1 u1 squared, because a half mv squared is your kinetic energy. That's the kinetic energy of ball 1 moving to the right, plus the initial kinetic energy of ball 2, a half m2 u2 squared, is equal to the final kinetic energy, a half m1 v1 squared plus a half m2 v2 squared. You don't have to memorize any fancy equations. You can do all the algebra later, but this is an equation that you can immediately write down. Kinetic energy before the collision is equal to kinetic energy after the collision. That's what conservation of kinetic energy means. And we can then write a second system of equations. If you are asked to find two things from the problem, then you'd need two equations. and that's the conservation of momentum. The initial momentum, m1u1 plus m2u2, must equal the momentum after the collision, m1v1 plus m2v2. So now I've got a system of two equations that I can immediately use to solve maybe for two masses or two of the velocities or whatever it may be. Two equations, and if I have two unknowns, then I can happily solve. So that's what an elastic collision is. Kinetic energy is conserved in an elastic collision. The other type of collision that we have is an inelastic one. Again, I mean, you could read further on these and see a lot more complicated mathematics and so on, but this is basically what you need to remember when you see elastic and inelastic. Is kinetic energy conserved? If it's inelastic, kinetic energy is not conserved. This is the more realistic scenario. The kinetic energy after a collision gets transformed into other sorts of energy, into elastic potential energy, heat energy, into sound energy, whatever. But the total energy is not conserved. Total kinetic energy is not conserved, rather. Total energy will be conserved. So there's an object, a ball moving to the right, m1, a ball moving to the left has speed u2 and mass m2. And after the collision, now this is a scenario that only happens with inelastic collisions. Only with inelastic collisions will you have two objects stick together and move off as one. So two billiard balls rolling off together, if they hit with the right velocity, they just move as one at the same speed v. So they both have the same speed. Now kinetic energy is not conserved. So a half m1 u1 squared plus a half m2 u2 squared is not equal to a half m1 v1 squared plus a half m2 v2 squared. So I'm immediately removing that equation from the scenario. But what can still be applied is the conservation of momentum. So when you're solving these problems, always start with the conservation of momentum. And if the collision is elastic, you can then also use conservation of kinetic energy. If it's not elastic, you'd have to find another way. So the conservation of momentum says that initially the momentum was m1 u1 plus the momentum of the second ball, m2 u2. And the final momentum is m1v plus m2v, or simply m1 plus m2. One big object moving together with the final speed v. So the equation looks slightly different to the one above, but it's the same idea. And so this is an inelastic collision. It's one in which kinetic energy is not conserved, but still linear momentum is conserved. And so this was all the important concepts on dynamics. If we were to go in detail, we could talk about this for hours and hours and hours, but make sure that you are solving problems using free body diagrams, using the idea of conservation of momentum, conservation of kinetic energy if you have an elastic collision, to be able to, I think dynamics is a very important topic because it allows you to take pictures and diagrams and ideas and convert them into mathematical expressions so that you can now look at a system as in a mathematical way and then get an idea, an understanding, an answer, and then apply it back to better your knowledge of that picture and the diagram, etc. So I hope this crash course was useful. If it was, please leave a like, leave a comment down below, subscribe to the channel if you haven't already. From me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.